So let's begin, please.
Hold it close.
Closer, okay? So an announcement before we begin, and that is if everyone could please turn off their internet connection. The room, there are too many people trying to use the wireless here, which interferes with the Zoom recording. And that means that people who are trying to watch a video after class who are sick today will have a good quality video to use. It also means that we have an archive of these lectures for the last 10 years on the Atkinson Center. Also means that won't be good quality. So if you could all please turn off your internet connection, I would appreciate it. Thanks. So today we have Professor Phil Milner, and he's in the Department of Chemistry and Chemical Biology. So Phil, turns out, grew up just south of here over the border in Pennsylvania in a small town. I looked on Google, it looks like it had less than 3,000 people, something like that. Then he went on to major in mathematics and chemistry at Hamilton College, went to MIT in grad school, and then he went to University of California, Berkeley, where he designed frameworks for carbon capture. More broadly, Phil's research works is concerned on the intersection of organic, inorganic, and materials chemistry, and has broad applications to human health, the environment, and climate. In particular, today he's going to talk about materials to capture carbon from the atmosphere. And this kind of research will lead to next generation family of low-cost, high-efficiency materials for CO2 capture. And as discussed earlier in the course, ability to capture carbon from the atmosphere is really essential to be able to achieve low climate targets. So thank you very much for coming in. Phil?
Thank you. You don't have to applaud. I haven't done anything yet. Can we change the main screen so it's in presenter view? Looks like it's... Okay, thank you. Great. I'm really happy to be here today to tell you about some of the work that my group is doing related to carbon dioxide capture. I'm going to take you through a couple of stories related to the design of novel sorbent materials for different carbon applications, including direct air capture of CO2, and try to give you a feeling for the current technologies we have and some of their limitations. So I think most of you are probably familiar with a plot that looks something like this, talking about the different types of greenhouse gases and their contributions to climate change. So the big one that's about 75% of human anthropogenic greenhouse gas emissions is carbon dioxide. And then, of course, methane, nitrous oxide, and fluorinated gases kind of make up the remaining quarter. And our lab has done research in different types of greenhouse gases. I just included some references here for you related to nitrous oxide and hydrofluorocarbon capture in particular. But today what I'm going to focus on is carbon dioxide, since this is really the biggest problem of all of these. And so when we're thinking about doing post-combustion or industrial carbon capture applications, what we're really thinking about is how do we remove CO2 from a mixture of other gases that includes usually primarily nitrogen, oxygen, and water, as well as some other potentially trace contaminants like SOx and NOx. And so an ideal sorbent material, we want it to have incredible selectivity where it grabs only CO2 from that mixture, lets the other ones go. It has incredibly fast kinetics, meaning it captures that CO2 very quickly. We can process a lot of CO2 in a short amount of time. We also want it to have very good performance in the presence of water. That turns out to be one of the biggest challenges for sorbent design, is that many materials would prefer to bind water over CO2. And that's something we're going to talk about a lot today as well. We need our materials to have, of course, incredible stability as well. We want to be able to capture carbon dioxide, removing the other gases, and then release the carbon dioxide for either conversion into value-added products or geological sequestration. But that means we're going to have to bind CO2 and release it thousands or tens of thousands of times. So our material must have incredible stability as well. And doing all of that, the tricky thing is, one of the big problems of fighting climate change is how do you make money off of it? Or at least how do you minimize the costs associated with it? And for carbon capture, the main energy input is actually that final step where we release the CO2. to regenerate our sorbent to capture more CO2. That's where we have to put in energy as heat or vacuum, changing the pressure. And that's going to be something up to 80% of the cost of running carbon capture. So I'm going to talk to you about some traditional carbon capture processes first. And we're going to end with thinking about how can we maybe use alternative energy sources like light, like sunlight, as a way to drive carbon capture. Just to make sure we're all on the same page of how we're actually going to do a separation like this, what we're going to do is have a mixture of two components, like say CO2 and nitrogen. We're going to flow them into an activated sorbent or adsorbent, which just means a solid material or potentially a solution. And that's going to be set, the kind of mixture there is set by our incoming stream, like air, like the emissions of a power plant. And what we want is that one of the two components binds much more strongly than the other. So in this case, A sticks to the column and B flows through. That means we can actually separate them from each other. And we run this separation until we saturate our column with one of the components. Usually it's going to be CO2 for carbon capture, and let the other one go free. And this is the part that's all the energy right here, is now we have to turn around and purge that bound gas back off of our column so we can do another cycle here. That's 80% of the energy right there. And the reason why is that typically we have to heat the material up or change the pressure to induce the gas being released from our bound sorbent material. So how do we do carbon capture right now? It's really dominated by one material platform, which are called amines. These are small organic molecules that contain the element nitrogen. And this is something we've been doing for over 100 years. We came up with this as a way to actually remove CO2 from natural gas. We have to do that in order to put gas onto a pipeline. And so we have iteratively improved the structure of these amines, modifying the functionality of them to improve their performance. But even after 100 years, our current carbon capture and sequestration, or CSS, capacity around the world right now is about 50 megatons. And that big circle there, these are to scale. That is how many gigatons of CO2 we need to capture to reach net zero emissions by 2050. So we are a little bit, we are less than 0.5% of the way there. And we have 20-something years to make up that difference. So that's one challenge for us, to think about how can we get from that little blue circle to the much bigger one. And a problem with amines is, this has been the dominant technology, they have a lot of drawbacks. I'll show you in just a second why we use them, but they have a lot of problems when it comes especially to that stability factor I talked about. Amines have a very high density of electrons, which means they're very prone to giving up their electrons, which is what we call oxidation. And so they're very, very prone to doing that in air. If you ever borrow an old bottle of amine from a chemistry lab, it usually is brown. It has some floaties in it. It's because it's been oxidized by air. And they also tend to be quite toxic. They're volatile, so they're prone to amine loss over time. And they also decompose from heating. And so as we try to cycle these materials, we often have to constantly be replacing them. And that leads to really high costs for operating an amine-based scrubber. So, okay, I just told you a bunch of bad things. Why do we use amines at all? They sound terrible. Well, one amazing thing they can do, though, is actually react with carbon dioxide reversibly and selectively to form what are called ammonium carbamates, that structure in the bottom corner there. So these actually form from two amines coming together. They attack a molecule of CO2 between them, and they lock it in place. And it's not until you heat it up or pull vacuum on it that it will release the CO2. So you can actually flow a mixture of nitrogen, oxygen, water through. The amine will grab the CO2, and then you can release it on demand. So that's great. So they have this fantastic kind of chemistry-based selectivity for carbon dioxide, but really, really poor stability and other properties. So that's what we want to try to improve upon in our lab. And so we've really thought about how do we move beyond these types of amine-based technologies towards other types of nucleophiles or electron-rich molecules that may be able to react with carbon dioxide selectively and reversibly. So we've really focused on, in particular, compounds that use oxygen instead of nitrogen to bind CO2, because oxygen-based molecules are less prone to oxidation. And so I'm going to share with you two stories from our lab about designing these types of oxygen-based sorbents for carbon capture, focusing on these hydroxides, which are one of the ways that we actually do direct air capture now industrially, and also these amine oxides, kind of a new class of carbon capture material. Okay, let's start with these hydroxide materials. And so people have been trying to use hydroxide to do carbon capture for almost as long as they've been trying to use amines to do it. And so we can actually do this with simple metal hydroxide salts like potassium hydroxide. And there are large-scale startups based on direct air capture using simple hydroxide solutions because they're very cheap. And they can also pull CO2 selectively out of air from a chemical reaction. But they tend to show very poor kinetics, very poor capacities, and other kind of drawbacks. And they often need to be heated over 800 degrees C to release that CO2. So they have even higher energy demands than amines. And folks have tried to overcome that limitation by putting hydroxides into polymers. What are these called? Anion exchange membranes, or AEMs. You can actually incorporate these OH anions, these hydroxides, into those and see if they can do CO2 capture. And they also have very slow kinetics and poor performance. So consistently, the problem here is like, how do you get the CO2 to the hydroxide so that it can react with it? And so our idea was, what if we take those hydroxide, those OH minus anions, and incorporate them into a porous support where there's cavities where CO2 can flow in and out through the material and actually be bound chemically at those hydroxide sites. This may enable us to get a high capacity for carbon dioxide, fast kinetics, and while hopefully maintaining the excellent stability of these hydroxide sites for CO2 capture. Of course, these would be much more expensive than simple hydroxide salts, but if we can get a massive increase in performance, that could be worth it. And really, when we started this project, the question was, how do you put an ultra-high density of hydroxide anions into a porous support? Nobody had actually ever really done that before, because hydroxide is very corrosive, it's very reactive. And so we want to finding materials that can survive being soaked in hydroxide even alone is quite difficult. So one way that we did this in collaboration with Alex Forrest at the University of Cambridge is actually using electrochemistry with what are called porous carbons. Carbons are basically charcoal. They're the most stable kind of porous solid that you can find on Earth. And what we found is that you could actually electrochemically charge in hydroxide anions into these materials and then pull them out, and they're ready to do direct air capture of carbon dioxide. And so we carried out a lot of tests to prove that they can do direct air capture. So on the bottom left there is a plot of cycle number versus CO2 uptake. That's pulling CO2 out of air. They have quite low capacities. That's because the hydroxide density is quite low, but they actually can work well. And you can even see in that middle plot there on the bottom, I do have a laser pointer here, this plot, that they actually can pull CO2 out of air as compared to all these control carbons. And the nice thing with carbon is it's conductive, so you can actually run a current through these carbons and trigger CO2 release without needing to heat them up. So this is a really cool approach to putting hydroxides in porous materials, but the problem is the capacities of these materials are very, very low. Just to give you some perspective on that, over here we can bind about 0.2 millimoles per gram. For amine scrubbers, that number is typically 3 millimoles per gram, so 15 times higher capacity than these carbons. And so that's really a challenge. How do we get an even higher density of hydroxides into porous materials? And so to do that in our lab, we've moved away from these carbons, which are amorphous, meaning they don't have any long-range order. And instead, we want to move towards well-ordered crystalline porous materials, which are called metal organic frameworks. So to make a metal organic framework, it's quite simple. You just take an organic component like this gamma cyclodextrin here. This is a cyclic oligosaccharide or sugar molecule. You can throw it in with metal hydroxide or different metal salts. It will actually crystallize out as this nice extended structure here. And what we're really after here are these cavities, those pores. Those allow CO2 to flush through the material very quickly, while inside of here are a high concentration of hydroxide anions that can bind the CO2 reversibly. Just to kind of simplify that structure down for you a little bit, this is really what that repeating structure looks like. It has metal cations holding it together. And here are those hydroxide anions that we're going to bind CO2 via bicarbonate formation. And so for a former PhD student in our lab, Mary Zick, started off this project by just figuring out, are those hydroxide anions in these cyclodextrin-based metal organic frameworks capable of pulling CO2 out of low concentration streams and potentially from air? The way we test that is we measure something called an absorption isotherm. So we're going to vary the pressure and look at the CO2 uptake And as you can guess from saying isotherm, this is going to be at a constant temperature. So in this case, it's 40 degrees Celsius, which is the temperature of most industrial emissions from power plants that contain CO2. And so she made these MOFs with many different anions inside their pores, from hydroxides to non-nucleophilic ones like chloride or acetate or benzoate. Those non-reactive ones show very weak CO2 binding here, not very high capacities at high pressures, whereas those with those hydroxide anions, these three up here, these all show very steep CO2 binding at low pressures, which is indicative of a chemical reaction, and also a very high capacity here at one bar of CO2 pressure. We can also support that those hydroxide anions are grabbing CO2 chemically using a variety of techniques, including something called solid-state nuclear magnetic resonance. I could probably spend the next 50 minutes explaining what NMR is, but essentially this is a technique that we can look at very specific atomic sites in a structure and zero in on which of them are undergoing a chemical transformation upon CO2 capture. So we can see that this signal right here is greatly enhanced in this MOF, indicating it has reacted with CO2 to form bicarbonates. And if we get rid of those anions that we think are responsible for CO2 capture, that signal goes away. So this really tells us the chemical mechanism by which we are achieving carbon capture in this material. So we can also look at this using something called density functional theory. This is a way to do theoretical modeling of atomic structures. So we can actually see here is our MOF structure, kind of a portion of it. There's that hydroxide anion. It has a water bound to it at all times, which is just along for the ride. And so when exposed to CO2, it forms this bicarbonate anion. And what's really remarkable about this material is that that formation, that mechanism is reversible. In most simple metal hydroxide salts like potassium hydroxide, that reaction is not reversible. If you heat them up, they will lose water instead of CO2. They'll form carbonate salts. They're really, really hard. Maybe you have to heat them up over 1,000 degrees to get the CO2 to come back out. But in this case, these isolated sites are reactive enough that they can lose CO2 upon heating just to 80 degrees Celsius, which allows us to save a lot of energy in a carbon capture process. We can use other techniques to look at carbon capture in these materials too. We can measure something called a thermogravimetric analysis, these absorption curves. So now on our x-axis we have time. So this is showing us CO2 uptake as a function of time. And we can see that our material shows really fast CO2 uptake. This is good because in the real world, you really want this to be on the order of minutes of contact time, so you can be swinging CO2 on and off your material constantly. And we also can see that the profile is unchanged after heating under air, for example, to test the stability. We can also cycle CO2 on and off this material hundreds of times. As I've shown you, I keep saying to you, that's really important. We want to be able to do that. So we can actually look at the cycle number here and the capacity over time, capturing and releasing CO2 over and over again, and it's really stable up to 120 cycles here. So that's promising for CO2 capture from a dilute stream, 15% CO2 and nitrogen, which is the composition of emissions of a coal power plant. And if you may be thinking, coal power plant, what is it, the 1970s? A lot of countries around the world still rely on coal as one of their dominant energy sources. In the US, it's kind of faded out. It's mostly natural gas now. We'll get to that in just a second. But in places like China and India, coal still makes up a pretty large portion of their energy use. So we still need better materials for carbon capture from coal power plants. They're actually the first thing we should go after as the biggest offenders for CO2 emissions on Earth. We can also look at CO2 capture using this technique called breakthrough. So what we really do here is we load a little column filled with MOF, and we actually flow a mixture of gases through, and we look at the effluent using this instrument here, a mass spectrometer. That allows us to look at the CO2 and nitrogen content of our stream as we flow through. And so what we're going to see is that as we flow the gas mixture through, nitrogen comes out so quickly we can't even detect it because the material has no affinity for nitrogen, it just lets it through. And CO2, this is CO2 being absorbed in the material, so there's none detected on the backside here. The material can still do carbon capture under humid conditions here, so we can pre-humidify the stream with water and the MOF, but it's definitely much worse than it used to be. And this is a big problem that we're trying to overcome with these types of hydroxide materials now, because with amines, they typically can work okay under humid conditions, while our materials show a diminished capacity in the presence of water. So to try to get at that, to see if we could maybe overcome that by making the CO2 binding even stronger in our material, we thought we might be able to change the metal salt that we use to make the MOF. Everything I showed you so far was with potassium, which is one of the cheapest metals on the planet Earth. But what we found from our calculations is that if we change that cation, which is right there, this metal cation, to something else, we can actually maybe change the thermodynamics of carbon dioxide capture in these materials. And indeed, excuse me, we did find that to be the case. So we could actually vary that cation from potassium, which is cheap, sodium and potassium are cheap, rubidium, a little bit more expensive, up to cesium, which is quite expensive. But if we do that, we can actually see a change in the CO2 absorption profile. And when we see it get steeper like this at low pressures, that means the CO2 binding is stronger, and also that it might be able to do direct air capture of CO2. So this rubidium one in particular looks quite promising for getting a high capacity here. And indeed, when we looked at this now using thermogravimetric analysis instead of these isotherm measurements, not only does this material show insanely fast kinetics here, where it binds CO2 within a minute or two, it can actually, if we flow 400 ppm of CO2 over it, it actually can absorb it now. So this MOF can actually do direct air capture. We really wanted to validate that it can do direct air capture, so we carried out a series of measurements, including, again, these absorption isotherms. Once again, we're varying the pressure, looking at CO2 uptake here. And so when we do that, we can actually look in this low pressure regime, which is kind of boxed out here, and see that if we draw this dotted line for the concentration of CO2 in air, 400 ppm, unfortunately, we have to keep updating that number every year in our lab. But right now, it's about 450. So if we do that, we can actually see this material has quite a good capacity for direct air capture. It also seems to be quite good for capture from natural gas combined cycle power plants, which is one of the dominant forms of power plants in the United States as well. That's about 5% CO2 and 40 degrees Celsius. So, excuse me again, to really validate that this material could do direct air capture, Alexandra in our lab actually built, that's kind of generous, put a CO2 sensor in a jar and put MOF into it, and you can actually see the CO2 content. That's the CO2 content in our lab starting out, and once you seal the jar, the CO2 content drops to 0 here. So this actually allows you to pull CO2 out of air in our lab. And we can just regenerate it by pulling vacuum on it, and we can do it a couple of times. So that's promising. We also looked at the cycling capacity here for direct air capture, so we can cycle it many times and it stays quite stable, both for direct air capture and also for carbon capture from a natural gas power plant. And if we go back to that breakthrough measurement, again, this is really showing that you can do the separation for real. We can flow now 5% CO2 and nitrogen, that's that combined cycle, natural gas combined cycle power plant emissions. And we can see nitrogen comes through again almost instantly, followed much later by carbon dioxide here. So it shows amazing selectivity. But once again, we have this same problem where when we add water, it gets a little bit worse. And so we see that the CO2 profile, this is what you want to see here. Nitrogen comes through almost instantly, CO2 at a much later time, but it's coming through faster, meaning there's a reduced capacity. And so we want to think about how can we solve this problem. Water is everywhere. Of course, water is in air, but it's also in all of these emission streams too. So we want to figure out how can we do carbon capture in the presence of water. And so one really simple idea we had to solve this was, what if we just heat the material up? You could imagine that if you think about water condensing on a leaf, right, like dew, that happens when it's cold and very humid outside, so the relative humidity of air is quite high. And so if you heat it up though, you'll decrease that proclivity of water to condense. So if we just heat our materials up, they should show improved CO2 binding in the presence of water. And that is indeed what we see. If we look at the CO2 capacities under dry conditions here, these blue bars, the CO2 capacity as you increase the temperature goes down. That's what you would expect for normal absorption. But for water, it actually goes up and maximizes at 100 degrees C, the boiling point of water, and then starts to match the dry one. So this means that we can actually do CO2 capture at high temperatures using this material in the presence of water. One last thing I'll say about these materials, though, they are still giving us many mysteries. When we looked at cycling now under hot conditions, You can see that under humid conditions, if we cycle at different temperatures, 90 or 100 degrees C here, it's pretty consistent. But for dry, there's a real big switch between 90 and 100 degrees. 90 degrees, you cycle very stably. 100, it drops off. The question is, why is that? And we've looked at that quite a bit. We find that the CO2 binding effectively is irreversible when you heat it up to very high temperatures under CO2 flow. So that's what this plot is showing, that it kind of, as we try to absorb the CO2 and then release it, it works okay until you get up above 100 C and it starts to become irreversible here. And we can also track this with a number of different spectroscopic techniques, including infrared spectroscopy. So this looks at vibrational stretching of molecules. So we can see that the vibrational spectra of our molecule changes over time. And we can also track it again using that technique called NMR that I showed you before, where again we see a change in the signal. And I'll really just, I'm kind of racing to this because I want to summarize for you what we concluded from all of this is an unexpected shift in the absorption process from this reversible bicarbonate formation. So these are hydroxides, these are bicarbonates, and the presence of CO2. But if we heat it up under CO2, we actually lose water and form these carbonates. And this is actually something that's known to happen with amines as well, that if you heat them up under CO2, they will actually form these ureas here. So this is something, again, we're trying to figure out how to overcome. It's a current challenge of these materials, but I think what we're pushing towards is something that could be really cheap, really stable, operate under humid conditions, and we're getting close to that point. Okay, let's see. That clock is not working here, so make sure I'm keeping track of time. Okay. Let me show you another story here about a different approach to make oxygen-based nucleophiles for carbon dioxide capture using these N-oxide hydrates. And so, as I mentioned before, why can't we solve climate change right now? Amines are just too expensive to use in industrial processes, and that's because they undergo oxidation. So they can react with the oxygen or O2 present in these gas streams and undergo an oxidation to make many, many, many different types of products. And so the idea that Zoe, joint graduate student with me and my colleague Tristan Lambert in chemistry, thought was, what if we could take advantage of this? Could we find an oxidized amine that can do carbon dioxide capture? Because if we could, this amine, this thing should be much more stable to oxidation because it's already oxidized, right? And so what we targeted was this molecule here called MMNO. The structure of it is not that important for today other than to just say it's an oxidized amine. And it's widely used industrially in the lyocell process to process cellulose. So it's already used industrially. And so it actually has incredibly high thermal and oxidative stability. I'll show you some proof of that later on that we measured ourselves. It has no known environmental hazards, basically the same price as any amine because you make these N-oxides from the corresponding amines just by oxidizing them. And they also are less basic, and that means they're not corrosive. So amines have all these issues where, for example, if you try to put them in steel, they'll corrode the steel, but these N-oxides are not corrosive, so they're much more compatible. And so the question is, can these N-oxides actually do carbon dioxide capture? So that's what we set out to study, and at first it seemed like the answer was no. This seems like a very silly idea because if you take CO2 and bubble it through a solution here, you actually don't see, you only see CO2. That's what this signal is for. And that's with this MMNO or with water itself, you see the same thing. But if you actually mix those two molecules together, MMNO and water, you can actually see the appearance of a new signal here, which is due to a species where you have reacted with CO2. And this is remarkable to us because this is kind of what happens with amines, but it happens because amines are very basic and they can react with CO2. This N-oxide is not basic, but it can yet still somehow react with CO2. It's also reversible. We can switch from a CO2 flow to a nitrogen purge, and that peak goes away. That means it's reversible. So we can actually capture CO2 and release it using this cheap, stable molecule. We carried out a lot of studies to understand the molecular mechanism for this process. So the first question is, why do we need water for this to work, right? That's kind of unusual. It implies that this N-oxide does not react with CO2 by itself. It needs water, which actually is okay. Water is everywhere in carbon capture, so it'll get the water, but we really wanted to understand, why does it need water? And so to do that, to study that, Zoe exposed this N oxide to different equivalents of water, and that allowed us to actually look at its kind of signature as it's binding water. And so what we can come away from that is realizing that this molecule likes to form both a monohydrate and a dihydrate as it's exposed to increasing concentrations of water here. You see an increase in the amount of this monohydrate and even this dihydrate here. So that just tells us water likes to stick to this molecule. I have structures here to show you that. So we can actually pull out the thermodynamic parameters here and understand that this molecule likes to bind water as a monohydrate and a dihydrate. This is the form that we think is responsible for carbon capture here. Okay, so now we can do the same exact experiment, except now in the presence of CO2. That was in the absence of CO2. So now we can actually see how does the presence of water affect the CO2 binding in this material. So again, we vary the water content. We look at the signal here. We can fit this data and extract out that we formed this new carbon species and its concentration maximizes at around 5 equivalents of water relative to the N oxide here. Okay. So what that means though is that as long as we control the water to N oxide ratio in an organic solvent, we can actually get carbon capture to occur. So Zoe actually found that we can just do it in water. This is deuterated water here, but it is basically water. And so you can actually just dissolve this molecule in water, bubble CO2 through, and it binds it. Something that is very common for amines again, but not for something that's not this basic. We carried out again those density functional theory calculations to try to get a molecular level picture of what's going on here. We were able to recapitulate all of our experimental findings about the formation of this monohydrate and dihydrate here, as well as these CO2 adducts. And what we think is that these are, again, forming bicarbonates, similar to what I just showed you can happen in those hydroxide-based MOFs, where we can react with water plus this N oxide can react with CO2 to form a bicarbonate species like this one here. That's a bicarbonate anion right there. So now the question is, can this thing work under realistic conditions? We've made this, it's a very cheap, simple molecule, but can it actually do carbon capture realistically? So to do this, we actually assembled a very complicated setup to do in situ monitoring of carbon capture with this molecule. So what we do is we flow the mixture of gases here into these mass flow controllers, these MFCs here. These allow us to control the exact flow rate of the gases. And we flow these into this IR cell, infrared cell here, and that allows us to watch different chemical changes as CO2 or nitrogen is exposed to our molecule. And so this is kind of a schematic up here of what this looks like. And we can actually see that we have our molecule before CO2, and after we add CO2, we see new signals appear, which go away after we switch back to nitrogen. And those signals really match onto a bicarbonate anion, showing, kind of validating our hypothesis of the mechanism of carbon capture in this material. We can also cycle it similarly to what I showed you cycling data before. We haven't done 100 cycles because Zoe actually has to do these by hand right now, so she stands there and switches CO2, and then like 30 minutes later switches to nitrogen. So we're working on that. And so after 7 cycles, we decided it looks like it's nice and reversible. But you can actually see we can cycle CO2 on and off this material quite readily. And something that's really exciting, and I think a unique opportunity for Cornell, and I'll talk about this at the very end of my talk, is that we actually have a power plant at Cornell. I don't know how many of you knew this. There's a natural gas-fired power plant on campus. It's kind of off onto the side. I can't even describe where it is. It's somewhere over there-ish. I don't even know where we are. So actually, yeah, whatever. It's somewhere around here. We have a natural gas power plant. We actually got some of their power plant emissions, the flue gas. And we found that our material can actually absorb CO2 from that flue gas. It's about 10% CO2. You can see that CO2 capture occur and then release. This even has a little bit of NOx. NOx is something that destroys a lot of carbon capture materials. This is one of the reasons you have catalytic converters on cars to get rid of NOx. And so it can destroy carbon materials, but ours seems to be totally okay with it. And something we're really excited about is that Zoe found that these N oxides show much better stability than structurally similar amines. So for example, if we take our molecule, this MMNO here, we boil it for a week in air. We can boil it under just air or under that flue gas that we got from Cornell's power plant, and amines will decompose. Excuse me. They'll form these insoluble products, they'll turn brown, they'll decompose. But our MMNO molecule is totally stable. So it has much higher stability than structurally similar amines, while not being basic or corrosive at all. So we're really excited about the opportunities here. We're hoping to keep exploring this, potentially commercialize the use of these N oxides as carbon capture materials with improved stability compared to traditional amines. So stay tuned for that. So my last few minutes here, 10 minutes or so, I want to talk about one last story from our lab, which is a little different. So everything I've shown you before so far, these have been new sorbent molecules, but kind of in a traditional carbon capture process, where we flow a CO2 rich stream through to capture the CO2, let everything else go, and then we release that CO2 using vacuum or heat. And like I mentioned several times, that release of CO2 is most of the energy cost of a carbon capture process. And so the stronger you bind CO2, the more energy you have to put in to release it. And so the question we had was, can we use an alternative energy source to actually achieve CO2 desorption rather than heat or vacuum? And in particular, our idea was, can we use light to do it? And so our energy diagram here would look something like this. We'd have our sorbent, we would excite it with visible light to form an activated sorbent, which would capture the CO2. And then again, we use light to release it on the other side. In this way, most of our energy input could just come from sunlight. And we could run almost a passive carbon capture process in this way, which is not something that anybody had ever done prior to Bayou's work in our lab. So we took some inspiration from nature to how to figure out how to pull this off. And so the way that nature actually utilizes the solar spectrum for energy production is actually using this carboxylation process in an enzyme called Rubisco. And so it uses this reactive functional group called an enol, this one right here in blue. This can bind CO2 here to fix it, and this is what plants use to make energy. And so we took some inspiration from that to actually think about whether we could achieve carbon capture using a similar mechanism with light-generated enols. And so Bayou looked into the, the organic chemistry literature and found that this type of motif here, these 2-methylbenzophenones or ketones, these actually can undergo a series of light-driven steps where they can actually capture carbon dioxide here to form this carboxylic acid here, this other functional group. You don't need to know the chemical details of how that works, but the long story short is it's a chemical reaction we can do where we use light and a simple molecule to bind CO2. But what we didn't know was whether it was reversible. The forward step was known, but the reverse step was not actually known prior to Bayou's work. So we started with just trying to figure out, can we actually do carbon capture here? We took this very simple molecule, 2-methylbenzophenone. This molecule, I think it's on the order of a couple of dollars actually per kilogram. You can find it online to buy, so it's very cheap. We can bubble CO2 through with light irradiation, and we can actually see if we look at time here versus CO2 uptake, we could see an increase in concentration of our CO2 capture product here. So again, this is what we want to say, that we've actually captured CO2 using visible light. But something really important to proving that is this kind of on-off experiment where you turn the light on and off alternately. So when we turn the light on, we capture CO2. When we turn the light off, it stays the same. Capture, release, capture, sorry, not release, capture, no capture, capture, no capture. This just tells us that you must have light irradiation in order to capture carbon dioxide with this system. But that was with pure CO2, which is actually industrially pretty useless to be able to capture. We need to be able to capture from dilute streams simulating emissions of power plants or even from air. And so Bayou found this system does work with lower partial pressures of CO2 down to 10% CO2 and nitrogen, again, close to the emissions of Cornell's own power plant. And we can also add a little bit of oxygen into the stream, which is also present in our flue gas, and it still works okay. And something that's a very difficult experiment to do in Ithaca, New York, is we tried to do it in the window cell of our lab. There's about 3 days a year where we could get this to work. It's a joke. It's not that far from the truth, though. But so we just used one magnifying glass to get the sunlight to hit it in our lab. Our lab's a little dirty over in Baker Lab, up where all the chemistry labs are. But we were able to actually see carbon capture driven by just natural sunlight using this process. And Bayou, I'll show you a little bit of data later on. It's a little bit more scientific, using a solar simulator to achieve the same thing. So now the question is, what about the release? And so, long story short, what we thought was that it would be very, very difficult for us to release that product that we're making, this what's called a carboxylic acid, this functional group right here. But we thought if we treated it with base, we would be able to achieve the CO2 release much more efficiently. And I'll say, long story short, as part of our collaboration with my colleague Andrew Musser, who's an expert in photochemistry, and his graduate student Kaiser, we're able to validate this mechanistic hypothesis that our molecule is able to mediate its own release of CO2 as long as there is some base present in the reaction mixture. And so what we found is that we can actually trigger this decarboxylation using base. So if we add some base here, we can actually deprotonate here and actually trigger the release of CO2, which is in this blue plot here. We have a lot more data than this, validating that only with a combination of light and base can you achieve CO2 release. And I'll say for all of you who are graduate students or thinking about going to graduate school, this basically never happens. But Bayou, one concern is that I've only shown you that base helps CO2 release, but there's a chance that it could ruin CO2 capture. But the thing that never happens in grad school is that when he went back and tried it with base, it actually worked even better. So it works better, very, very lucky that the presence of base, which we need for the CO2 release, actually enhances the CO2 capture in this system as well. So putting this all together, what this means, if we take this cheap, simple molecule here, we add some base, when we have a CO2-rich stream, we should capture it preferentially. And when we switch to a CO2 lean stream like nitrogen or pull vacuum, we can release the CO2, also all under light irradiation. So Bayou was able to do that using this simulated carbon capture process here. So we're capturing and releasing. We set ourselves kind of as a limit of 15-minute cycle times because we wanted to be really, really fast. In theory, if we absorb for longer or desorb for longer, we could have an even higher working capacity for our system, but we wanted to kind of keep it quick. And so we were able to do this with a simulated flue gas stream, and again, using some flue gas from Cornell's power plant. We actually go there and we have basically a garbage bag that they fill up with gas, and we just run up to lab and use it as quickly as we can. And we also, everything here so far has been using 390 nanometer light, which is essentially blue or violet light. And so we wanted to make sure this could work, again, with sunlight. So Bayou used a solar simulator here, which we actually borrowed from Tobias Hunrath, to actually do this and to show that we could release the CO2 using simulated sunlight. I'll just put up the mechanism here for those of you who are interested in the chemistry side of this. So likely it proceeds through a series of steps where we actually capture carbon dioxide through what we call photoenolate, this intermediate here. That's how we achieve the CO2 capture. And then when we shine light on it, we can actually release the CO2 through a series of steps here and ending with a final protonation step. So again, this is the the first example of a fully light-driven carbon capture process where light is used for both the capture and release. So really, we have a lot of work ahead of us to figure out the engineering constraints. How do you actually do this on scale? How are you going to do this in a way that's actually practical? But you start to get to the dream where you could imagine putting a field of solar panels out, somewhere in Texas or Arizona or something, and they're just passively pulling in CO2 from air and capturing it. So that's kind of the final dream here if we can get it to work. One last thing I want to say about Cornell's part of that dream is we have something really cool and new that the Atkinson Center has actually supported Tobias and I and Grishma Godakota from civil engineering is something called the Capture Lab. And I can never remember the acronym, it's up there. We came up with an acronym that spells out capture. But it's a capture lab where what we're trying to do is attach actually a trailer to Cornell's power plant so people could actually get ready access to samples of flue gas. This is really hard to do right now in our current funding and sort of political climate and everything. Like, you'd have to go to a real power plant and say, please, can I have some of your flue gas? I promise I'm not trying to steal any industrial secrets. I just want to test my carbon capture material. It's very difficult to do, but now we're hoping that we can create the first kind of academic flue gas sampling station in the world right here at Cornell. So We're hoping to get that online in the next year. And again, like I said, that's supported by the Atkinson Center for Sustainability. So we're really excited about that. And I think really once we get this online, integrating this into all kinds of sustainability and carbon capture research and classes at Cornell will be really, really awesome. So with that, I have to thank my wonderful group who did all of this work. I've been saying their names throughout. Most of this work has been supported by the Department of Energy, the National Science Foundation, and a couple of nonprofits, including the Atkinson Center for Sustainability, and also the Carbon Tech Development Initiative through New York State. And with that, I think I'm roughly on time, and I'd be happy to take any questions that you have. Thank you.
Do you want to ask the questions?
Yeah,
Microphone up.
Yes, I can.
Fine.
It's right there, I think. Is it here, the microphone?
There it is.
Yeah. Okay. Do you just want to run up to people?
Yeah. Do you want to point or?
I can pick if you want me to. I'll start. We can start down here.
Okay.
Hi, thank you for speaking with us. You just briefly mentioned it, like with the current political climate. I was wondering, with regards to carbon capture in general, what is the main framing that is being used to make investing in these like new processes and like all of this testing attractive to investors and politicians to try to make it more large scale?
Yeah, great question. So the question is about how do we encourage investors? How do we frame all of this carbon capture research? And I think the tricky thing with CCS, carbon capture and sequestration, especially from post-combustion, is that's really difficult. It's hard to make money off of CO2. You can try to turn it into valuable products. Turns out it's not that useful of a chemical, or sell it to soda manufacturers, but that ends up back in the air anyways. So I would say carbon capture and sequestration is a tough sell on that front. It's basically what you can sell the CO2 for. So that's where I think that direct air capture has a lot more current, some political support, and especially in kind of the startup and sort of tech industries, because there you start to be able to get into a market of carbon credits. Some of that could be from governments, putting a cap on carbon capture, and some of it is companies voluntarily doing that too. So for example, imagine you're Google and you have made a pledge that you will be net zero by 2030. You don't make anything. How are you going to cut your carbon emissions? Most of Google's carbon emissions, for example, come from their servers running and then their employees, right, in their buildings. So they would want to go to a company and just give them money and say, please capture carbon on our behalf. That's a market that you are starting to see emerging for direct air capture as a way to say, okay, we charge you $300 a ton of CO2, we can sequester on your behalf. So I think that's one market that is kind of not even supported by the federal government, right? Some of that's just pressure from consumers on companies to say, and of course governments to do that too. So New York State has pledges like that, right? How's New York State going to cut all their carbon emissions? Some of them are, unavoidable. So I think that's one way that you can do it. And the other is, what do you do with the CO2? And that's the tricky thing, because it's hard to turn it into very valuable things, but that's why there's a lot of great research, and some of it done in this department in chemical engineering, specifically about carbon conversion into, say, jet fuel or polymers. In chemistry, we have people who research how do you make plastic out of CO2. So, and Grishma's research is how do you make buildings out of CO2. So then you could sell the CO2 for something, right, and recoup some of your costs. But in order to make that all work, you need the carbon capture to be as cheap as possible, right? If you're spending $100 a ton of CO2 and you can only sell the CO2 for $20 a ton, you're losing money. But if you can capture it for 20 and sell it for 100, you can now make money, right? So that's the tricky part always with carbon capture, yeah. It's a really good question. And I probably just revealed how I'm a chemist and trying to answer it, my very naive understanding of the market, yeah.
You mentioned that for rubidium, that at 100 degrees Celsius, it drops off for cycling. I was wondering, how do temperature limits for irreversible binding for like other?
Oh yeah, good question. So amines actually could not get anywhere near 100. They would decompose and they would likely not even bind the CO2 anymore. So there's a couple of different temperature regimes which are good for carbon capture. I kind of focused on the lower end. So room temperature is obviously direct air capture. Flue gas from power plants is typically cooled to extract as much of the energy out, the heat out as you can, and also so that the stream coming out doesn't kill all the birds that fly over all the power plants. So it's usually about 40 degrees Celsius. But the emissions, say, from cement and steel manufacturing, which is, I would call unavoidable emissions that we're never gonna, it's very, very hard for us to get rid of, those come out at, say, 100 or 250 C. They're an interesting target right now for a lot of folks, and amines absolutely cannot do it. So I guess that's a unique advantage of these hydroxides and other types of high temperature sorbents is you can go after those kind of streams instead. So yeah, it's a good question. Traditional systems would not work for high temperatures like that for 100 degrees. Yep. I guess the cement and steel folks don't cool the stream, but the birds that fly over just get wiped out, I guess.
So I was just curious, what does the timeline look like for commercializing the use of MMNO?
Is Zoe in the audience? You can ask her. I think that with carbon capture, I'd say, like kind of what I was alluding to previously is with the current situation, and especially with the way startups are right now, direct air capture is kind of the hot target. So that molecule can't quite do it yet. And if we can get it to the point where we could do direct air capture, we probably could start rolling it out within a few years. So I'd say that's kind of one just reality at the moment. And you think about post-combustion carbon capture is like a noble goal. We should capture all the carbon dioxide coming out of our power plants right now, except nobody wants to pay for it. And so that's the tricky selling point on that kind of approach. It's really important fundamentally. And if the political reality changed, the government put carbon taxes on every power plant in the US tomorrow, then we would need the technologies in place. So I guess that's kind of the trickiness is right now, direct air capture, and especially in the US, is kind of the way to go. And so that's where we're pushing to get to. So if we can get that to work, then we will be in shape within a few years maybe to be able to commercialize it, yeah.
So why do we need to re-release the carbon? Is that just for like making it financially profitable? Is there other reasons?
So you can do irreversible carbon capture, so I guess we would call that sequestration. So what it means is you bind the CO2 once, and whatever you turn it into needs to be valuable itself. So that is actually what Grishma's Godakota's work is about, is converting CO2 into carbonates, which can be used to make cement, for example, or concrete. So that's where you just do it in one shot and you just get something valuable. Most of the time, what we want to do is capture, and we want to be able to use the same, if you imagine the tank I talked about at the very beginning, you want to use the same tank to capture 1 million tons of carbon dioxide. That means you need to fill it up and then regenerate it and reuse it many, many, many times. So if you want to cycle a sorbent, you need to be able to release the CO2 back off. Whether you release it by heat or vacuum or light, or you release it by turning it into a chemical, which is also something that's possible. We call those reactive separations, where you bind the CO2 and then turn it into, say, a polymer, into plastics, then that's just kind of a different way of configuring it. So I guess the short answer is, if you're using something like rocks, enhanced weathering, for example, or like where you make a metal oxide, you can definitely just capture the CO2 and make metal carbonates and be fine. If you want to capture with the same kind of tank of chemical thousands and thousands of times, you need to be able to capture and release over and over again. Yeah.
My question is, when you are like re-releasing it at the end, what happens to the carbon dioxide?
Yeah. That's a good question. I think there's two main answers. What do we do with all the carbon dioxide? The first is you convert it into something, and the second is you sequester it underground. The geological sequestration, people have done the calculations and shown that there is enough capacity across the earth to store all of our carbon dioxide for the next 100 years. It's a very unsatisfying answer, but it is kind of the practical one, which is essentially we capture it and we pump it into caves and seal the caves as stone. So that's sequestration. Conversion sounds much more attractive, and it's a way you can make money, right? Nobody's going to pay you to fill a cave with CO2. At least, I guess if somebody offers to pay you for that, you should maybe run away, because I don't know what they're up to. But if you could turn it into something that you could sell, you could recoup your costs and maybe even profit. The tricky thing is, and there's one big problem, which is scale. So we as a species emit something like 40 gigatons of CO2, and we don't use gigatons as a unit for anything we manufacture chemically, except maybe for things like asphalt and cement and concrete to make buildings and roads. That's maybe where you get into the gigaton range. Otherwise, even plastics, we're still in the maybe 100 megaton range. So if you made, I think, I always forget the exact numbers, but if you made all of the top 10 chemicals produced on Earth out of carbon dioxide, some of which are ridiculous because they don't contain any carbons or oxygens, it still would only be about a third of all global emissions. So we have the volume of CO2 we release is so much that anything we figure out how to make profitably out of it would destroy the market for whatever it is that we make. So it's really kind of a tricky thing with the conversion. Now, that being said, I think we should figure out how to make as many things out of CO2 as we can, because it's basically free from air if you can pull it out, right? And you're doing some good along the way if you can do that. So I think that's kind of where you get into the realm of subsidies, right? If you say, okay, we will charge soda companies that if they make their own CO2 to carbonate their soda, we'll charge them one number, but if they pull that CO2 out of air, it'll be cheaper. Then you start to be able to make the economics work again. So it's a really long answer to your question. I think it's a tough question, and probably we'll need 1,000 answers to work out. We'll have to turn it into as many products as we can, and also figure out how to be okay with sequestration as a solution. I think that's kind of what I was mentioning. Some of the direct air capture sequestration market right now is literally it's almost like just for your conscience, right? Like if you want to just pay somebody, please capture my CO2 emissions, that's the way you would do it. You would sequester it, yeah. But it's a really tough question. It needs many, many, many people thinking about what to do with all the carbon dioxide.
My question is, do you think that in the future, then it would still be important to capture other greenhouse gases, and would that be done in like a similar way?
Yeah, I think so. I think each of them is an interesting, unique challenge because of the industrial sources, which I didn't really touch on much for any of the others. For CO2, a large chunk of it right now is energy production. That's combusting coal and natural gas. But a large chunk of it's also unavoidable emissions like steel and cement manufacturing. Those are kind of the big four for CO2. But for the other greenhouse gases, they come from different places. Nitrous oxide, for example, N2O, comes almost mostly from farming, from agriculture, from fertilizers. And so how you figure out how to capture it, you either need to go into farm fields and put up giant tanks that suck it up, or you need to figure out how to change the fertilizers that we've used for 100 years, right? Methane is a really, really big problem. There's some estimates in the United States that methane is now a bigger problem than CO2 for our greenhouse gas emissions, because we use so much natural gas in the United States and our pipelines are old and leaky. So all that methane leaks out, and it's actually 40 times more potent a greenhouse gas than CO2. So methane, how are you going to capture that is a big problem. The fluorinated ones are an interesting case because I think, we didn't talk about any of the I guess none of you have asked me yet, how do you know climate change is real? Maybe you're all believers. But one of those four greenhouse gases you can incontrovertibly prove is man-made because there's no natural sources of it, which are the fluorinated gases. They come from things like semiconductor manufacturing, refrigerants. So the refrigerants we used to emit, the CFCs that destroy the ozone layer, we replace them with HCFCs and HFCs. Those are greenhouse gases. Now we're trying to replace those with flammable gases. So just FYI, air conditioners may become filled with flammable gas in the future, but at least they won't cause climate change. You can debate whether the trade-off is worth it or not. Those ones are pretty nasty because their lifetimes can be hundreds to thousands of years. So every time we emit a molecule of something like fluoroform or sulfur hexafluoride, it's going to be here long after we're all gone. So I think that capturing those at their emission sources is important too. It's a really long answer, I guess, just to say yes. Capturing all of them, I think, is something to worry about. I think methane, if anybody out there is looking for the big challenge, I mean, we haven't even solved carbon dioxide yet, but we at least have some ground. Methane, we have nothing. There's like no solutions. Nobody has any ideas other than find leaks and try to plug them. That's our plan. So methane is a good one to think about, sensing it, capturing it. We have no good plan in the United States or anywhere in the world for how to deal with it. I think it may overtake CO2 in 50 years from now. Yeah. If civilization still exists. Yeah. Go ahead.
So, assuming that we plug all the CO2 into the earth, and the earth has the capacity to hold it for the next 100 years, as you've said, is that enough time for us to maybe save the planet from at least CO2, if nothing else?
I hope so. No, I think the answer is yes. It would give you time. I mean, so this is a good question. It's kind of alluding to a point that I'd like to make, which is why even think about doing CCS at all, capture from power plants? Aren't we just going to get rid of all power plants? I mean, eventually, I think we will probably get rid of most power plants, right? We may still need them for niche, high power kind of demand things or whatever for emergencies, but mostly we're going to get rid of fossil fuels, replace them with solar, wind, nuclear, who knows, fusion. So I think give a society 100 years, we'll probably not really be burning fossil fuels anymore. And so I think that it would give us time for the climate to stabilize. At least that's what a lot of models assume. There's also an interesting argument about the fact that with current population growth, the population of the world is supposed to peak at some point soon. That will also kind of contribute to somewhat to this. So I think the answer is probably yes. But why we need to think about carbon capture now is that transition from fossil fuels to sustainable energy sources is going to take maybe 50 years fully or 100 years. It's not going to happen tomorrow. Even if we wanted to, we could not fully switch to solar tomorrow. I mean, I already make jokes about Ithaca. Not sure how you're going to power all of Cornell with solar energy right now. The sun comes out only 3 days a year. So it's kind of we need time for that to happen. And that's why I think carbon capture buys us that time to figure out how to make energy more sustainably. Yeah.
So you mentioned that these different kinds of molecules that capture carbon, so like from the old ones like the amines and then the new hydroxide-based ones.
Yeah.
So after a certain number of cycles, which is lower for amines but a lot higher for others, they kind of stop capturing carbon. What happens to those molecules? Like, do they decompose? What do they do to the environment?
Yeah, that's a really good, I think with amines, I can answer that for sure. For most of the stuff we've done, we don't actually know very well yet how to answer that question. But for amines, people have been studying that for a long time, done a lot of life cycle analyses and stuff. So that's another problem. Amines themselves, I said they're volatile. Some of you may not know what that means. They're very easy to turn into like gas. And so they actually are a source of amines and ammonia emissions, which are very toxic and destructive to like wildlife, to especially aquatic life. So amines are not great even, they slowly degrade, whatever, we have to replace them. But what they release in addition to CO2 is also pretty nasty stuff. So I think with amines, a lot of times, then we probably would just put it in a dump somewhere when we're done with the amines. So I think amines are tricky in that regard too. Their life cycle analyses are not the best because amines themselves tend to be often like toxic to aquatic life, for example. So I think that's something to watch out for always with these systems. It's hard to judge though, if you're gonna cycle an amine 100,000 times, it's really hard to do that with real flue gas or real, air, cycle it many, many, many times and see what it turned into. So it's a hard question to answer, but it's an important one. Amines do not have the best profile for being released into the environment. You do not want to go put a bunch of amines in BB Lake, let me tell you. The fish will be dead. Yeah.
I just had a question. I was curious whether or not your research has brought you across like mycorrhizal fungi, and if as a mitigant for some of the environmental stresses of like raised temperatures.
No, it has not. I guess not. Yeah. Well, we can take an eye out for that. Yeah. There's maybe one more question in the back there.
Hi, thank you for your presentation. I was curious, going back to the carbon capture driven by sunlight, the setup for that. I noticed in your laboratory that you had the sunlight focused, and then later on you had the solar simulation. And I was curious if that also concentrates the sunlight, and just in general, whether or not the concentration of that sunlight matters, or if it can be used in open sunlight.
Good question. Yeah, so the concentration of sunlight definitely matters. With the solar simulator, we never went above, we did that at 1 sun of irradiance. So usually when you dial those in, it's kind of like, 1 sun's worth of irradiance. So we tried to be realistic there in terms of that. So how the technology behind solar concentrators and things has really been looked at a lot for photovoltaics, like solar cells. So there's a lot of solutions out there for how to concentrate sunlight, like kind of how we did. So our vision would be ultimately what this thing would look like is probably a solar cell, except it can flow gas through it, kind of like a porous solar cell, which doesn't really exist yet, so we have to build it. But I think that's kind of what we tried to do, was simulate that as closely as possible using sort of natural sunlight or 1 sun irradiance. And I think where a lot of this, where we kind of did some rough calculations, is we could capture a reasonable amount of carbon dioxide using maybe like an acre in West Texas. If you've never been to West Texas before, it's not like there's anything there. So we can definitely put some solar cells in fields and pull CO2 out of the air there. So I think that's kind of where the places where you might be able to do this is Texas or Arizona, that kind of, where there's a lot of sunlight. Yeah.
Hi. Thank you for your presentation. Would you say carbon capture props up the fossil fuel industry? Do you view it as a Band-Aid solution? And if so, what solutions should it work in tandem with?
Yeah, this is kind of getting back to what I mentioned about why do we need CCS? Because I think this is a great political discussion. We can debate it, and I think it's good to chat about it a lot, because that is the two sides of the story you'll hear. And if you go look on, any Reddit thread about this, you'll see both sides, right? Capturing the carbon dioxide from coal or even natural gas, I'd say at this point coal is, it'll become online so late that it's not really worth it. Natural gas is where to go, because it's going to overtake, natural gas will overtake coal in contributing to global CO2 emissions around 2032, I think. So in the next 10 years, natural gas will be the problem. So does doing carbon capture from a natural gas power plant mean that we will just keep using natural gas and thus delay the adoption of sustainable energy technologies? Or does it buy us time for the planet not to burst into flames? I tend to believe in the second one, because if you look at, and a lot of this is from reading papers actually from, nonprofits and sort of think tanks that focus on this stuff, they all sort of suggest that we just physically cannot switch to sustainable fuel energy sources fast enough. Even if at the best, we invest as much money as possible into solar and wind. You probably guess that's not happening exactly at the US right now. We're shutting down windmills in the US. But if we did it at the fastest possible pace, we still would not be able to fully transition until like 2080 or so, all the way over to sustainable fuel sources. So that means that in reality, it's going to be much later than that. So I think the point is, are we going to just, while that happens, we're going to just keep burning natural gas and kill the planet while we're doing all that work? I think it seems a bit silly if we could develop the technology. So to me, I think we should try to develop them both maximum funding, maximum involvement, to try to remove the emissions from power plants, because I think we're not going to get rid of fossil fuel power plants before 2100. So, but it's true that some people may use that as an excuse to say, well, maybe we never have to get rid of power plants then. So I think that's something that's hard for a scientist to be able to say. To me, it's just, if you look at the numbers, we're going to need to burn fossil fuels for the next 50 years. We can either release all that CO2 into the air, which is what we do now, or we can figure out how to remove it all as we transition to sustainable fuel sources. So that's, I guess, my opinion on it, but I do think it's a matter, somewhat of opinion. It's a good debate to have. Will the fossil fuel industry use this as an excuse to keep burning fossil fuels? They probably will try to. It's in their interest, right? And so I guess the question is, what's in the best interest of the planet? So I don't know. It's usually, a lot of this is projections and modeling, and the projections and modeling I've read suggest we're going to be stuck with fossil fuels for the rest of probably all of our lives. So we either can just keep burning them as we are, or we can try to make them be a little less bad. Yeah. And that's why I think also natural gas, it ultimately will help. Natural gas per sort of unit of energy it produces less CO2 than coal. So the global transition from coal to natural gas is a good thing. At least that will solve one aspect of it. It's actually like a quarter less. So it's actually, or a third to a quarter less. So it's much better. Yeah.
Thank you for your presentation. I also have one quick question.
Yes.
About direct water capture. From everything that I've read, it seems like as a global sink of CO2, direct ocean capture could be potentially useful, especially with like wave power being used on the spot potentially to power it. Is the technology there the same with hydroxides and potentially amines, or would it be something different?
I think it's usually actually pretty close to the hydroxides. So usually the basis of this DOC, it's called direct ocean capture, is you use electricity to generate those hydroxides, or you just use the ones that are naturally in the ocean and then regenerate them with electricity. It sounds like a cool technology. We've been looking into it a little bit in our lab, and right now the cost is way out of like scale for how it could be useful. But if it could be brought way down, it could actually have a chance. Yeah, I think it's definitely an interesting approach to look at, but with current technologies, it's really, really expensive and inefficient. Yeah.
Okay, so let's thank Phil again.